So we're going to try to make this reaction spontaneous. Right now it's highly non-spontaneous. Sometimes we can do it, sometimes we can't. We can take a look at this one and see. And so in order to figure out a temperature, we'll try that first under standard conditions. Okay, to try temperature under standard conditions, we know that delta G naught, that is delta G under standard conditions, can be altered by just changing the temperature. By changing the temperature, we can make the entropy term grow or shrink, and hopefully it could cancel out an unfavorable delta H if that's the problem. It's not always the problem. Let's figure out what delta H is first, and then see. When I look at this reaction, delta H for this reaction should just be the, you see it? This is the reverse of a formation reaction. And so delta H for this reaction should just be the negative, you know, Hess's law says if you reverse the reaction, you change the sign. The negative of the delta H of formation for CuO. Or we could just use Hess's law, you know, products minus reactants. And so what is the delta H of formation for CuO? Vincent, can you look it up again?
So, sorry. Which
CuO. Delta H for CuO.
Negative 157.3.
Okay, so that's going to be positive 157.3 kilojoules. It's backwards reaction. And that's per mole, and we're forming a mole. So that's not favorable. What is delta S? Delta S is going to be the entropy of the products minus the entropy of the reactants. And the entropy is going to depend on how much we have. So what is the entropy for copper?
Plain copper?
Yeah, just copper metal. It should be pretty low.
33.45.
33.45? 15? Which is a pretty low entropy. Copper is pretty simple, pretty well ordered solid. Joules per Kelvin. Plus, what is the entropy of oxygen, O2 gas?
That's gas right here.
205.03.
205.03. All right, but we only have half a mole. We don't have a full mole. And this entropy is what we call positional entropy. That is, you know, when we go back to the Boltzmann equation for entropy, you remember that? The entropy is equal to K ln W, where W is the number of ways you can arrange the particles. And so over here, we call this term the positional entropy. That is, you know, how many different ways can we arrange those particles in three-dimensional space. And delta H, we call the energy, but delta H is related to the entropy as well, but it's not the positional entropy it's related to. It's related to the, not the potential, but it's related to the potential. Potential what? Potential, gravitational potential? Chemical potential? Or, yeah. In other words, delta H is related to energy entropy. And so over here, delta S is positional entropy. Delta H is a measure of the energy entropy, because if we have an exothermic reaction, the exothermic reaction is dumping out heat. Heat is a high entropy form of energy or a lower entropy form? A higher entropy form of energy. And it's more difficult to utilize versus chemical potential energy, which is a lower entropy form. And so this is going to be related to the, what we call the energy entropy. Delta S is related to the positional entropy. Now, for positional entropy, that's going to depend. I mean, if we only have half a mole of O2 versus a full mole, you know, a full mole is going to have a lot more positional entropy than a half mole. And so what we have to do is we have to divide this by half or multiply this by half. divided by 2 or multiplied by half, I should say. Half as much entropy for half as much O2 gas. All right, minus the entropy of CuO. The entropy of CuO where should it be? You know, when we think about positional entropies, we think solids typically have a positional entropy or entropy of around 0 to 100, right? Liquids, 100 to 200, and in gases, yeah, greater than 200. Now, there are some outliers there. So, for example, water. You know, liquid water has an entropy below 100. It's like 67. That's fairly low. That's in the solid region, which means that liquid water is more ordered than your typical liquid or less ordered than your typical liquid. It's more ordered. So why would liquid water be better ordered than your typical liquid? Less possible orientations because of strong intermolecular forces. In other words, strong hydrogen bonding interactions. And the strong hydrogen bonding interactions are going to orient the water molecules in a certain way, like magnets would orient. And so there are gases. You know, when we think about gases, all the gases are somewhat similar. For example, you know, NO versus NO2. NO and NO2 had roughly the same entropy, around 200, right? But which one had a slightly higher entropy, NO or NO2? NO2 had a slightly higher entropy. And so the primary entropy results from gases. When we think about an ideal gas, it could be anywhere in three-dimensional space. And so thinking about that, you got that positional entropy there, but then when you look at the molecules themselves, NO has 2 atoms, and so you could have vibrations and rotations of that, versus NO2 has 3 atoms. And so 3-atom molecule is going to have higher entropy than a 2-atom molecule, but not by much. I mean, I think the difference was about 5 joules per Kelvin. And since gases all kind of have the same entropy value, there's something called Troughton's law. Have you heard of Troughton's law before? I didn't really talk about Troughton's law because it's not that, we aren't going to use it that much. There's, I think, one homework problem where you might use it. And what Troughton's law says is this: the delta S of vaporization, that is, the entropy change in going from a liquid to a gas or vapor, for your typical liquid is about 87, 88 joules per Kelvin mole. And that works because all the gases have somewhat similar entropies, and a lot of liquids do. But there are some outliers, like, for example, water. You know, water fails Troughton's, they don't call it a law, they call it Troughton's rule. But water would be an exception to Troughton's rule because the entropy change is greater. Anyway, we need to think about these numbers, and this is one way of thinking about the numbers here. All right, so the entropy for CuO, I'd expect that to be low, you know, less than 100. That's fairly simple, you know, just copper ions and oxide ions. And so I'd expect it to be fairly low on the lower end side. Can somebody look up CuO? Solid?
I got it.
Just S. 42.63. See, just a little bit higher in entropy than copper metal. Units here, joules per Kelvin. And so what is the entropy change?
.03.
93.03 joules per Kelvin. This is good. This is favorable. And this is unfavorable. And so what we have here in our delta G naught equation is we have this plus 157.3 kilojoules that's preventing reaction minus T. Okay, we're going to convert this into kilojoules. So 0.093 kilojoules per Kelvin. And so what we do is we just have to increase the temperature so that we can cancel out this unfavorable enthalpy. What is that temperature? Well, the temperature is just going to equal delta H or delta S. In other words, 157.3 kilojoules over 0.09303 kilojoules per Kelvin, which means the temperature should be raised to
1690.85.
1690.8 Kelvin.
Yeah.
All right, is this okay? Because you know the delta H, we got that from appendix D. The delta S we got from appendix D. But appendix D is good for what temperature? Yeah, in other words, 298. This is at 298. But we should be using the delta H and the delta S more like at 1700 Kelvin. Is this going to be okay? And we would say yes. We're going to say that delta H and delta S don't change much. And so this equation looks okay. Since we aren't using the correct values, we're just going to say it's about 1690 Kelvin, 1691 Kelvin. Is this temperature achievable? Yeah. That would be around 1300 degrees C. Is that correct? So we could do it. It's achievable, but to heat it up to about 1300 degrees C is going to cost you a lot of money. And so maybe there is a better way to do this. It's a fairly high temperature. Alternatively, you know, it would be nice to do this at room temperature so we don't have to buy an expensive furnace or oven. And so the next part of this is, yes, this was a reaction we could make spontaneous by increasing the temperature, but could we leave the temperature at 298? And so at 298 Kelvin, is it possible to make it spontaneous? Well, if we don't change the temperature, then the only thing we can change is what? The pressure or the concentrations. In other words, we have to go non-standard. And so the non-standard delta G equation is delta G non-standard is equal to delta G standard plus RT ln of Q. Now, when we're under standard conditions, what is Q equal to?
Okay.
Just under standard conditions. Q, give me the numerical value for Q. It might not be K. It's only Q is equal to K when delta G naught is equal to 0. But what is Q? Q is the products over the reactant. Under standard conditions, what are the pressures or concentrations of the products? All ones, you know, 1, 1, 1. Under standard conditions, what are the pressures or concentrations of the reactants? All 1. And so under standard conditions, Q is equal to 1. The natural log of 1 is 0. 0 times this is 0. Meaning that delta G is equal to delta G naught, which makes sense because we're under standard conditions. If we go non-standard, then it's going to deviate. And so we're going to go ahead and do this under non-standard conditions. what we want to do is we want to make this favorable. In order to make this favorable, right now it's unfavorable because at 298 Kelvin, delta G naught was like minus 130 kilojoules. Well, not minus, plus 130 kilojoules, which is highly non-spontaneous. And so what we want to do is we want to bring that down to 0. So if we can get delta G down to 0, then there's a chance we can go negative. Right? And so we set delta G equal to 0, which is equal to delta G naught plus RT ln a Q. But you know, when we're at delta G equals 0, we're at equilibrium. And at equilibrium means that Q goes to K. And so we get delta G naught is equal to minus RT ln of K. So what we're going to do here is solve for K. K is equal to e to the minus delta G naught over RT. K for this reaction is going to be the activity of the products. And so the products are going to be Cu, solid, times the activity of O2, gas. But O2, we just have a half mole, so we have to raise that to 1/2. Divided by the activity of CuO, solid. The activity of pure solids is 1. The activity of O2 gas is just equal to the partial pressure of O2 gas to the 1/2. And so here, when we go non-standard, the only thing we can change is the partial pressure of O2 gas. We can make it smaller, we can make it bigger to see if we can alter. All right, so let's go ahead and plug in our values. Delta G naught, what was that? Minus times a plus 129.7. But I'm going to write this in joules. So 129,700 joules. R is 8.3145 joules per Kelvin. T is 298 Kelvin. We're trying to do this under room temperature. And so, well, wait a minute. Am I making a mistake again? This delta G naught, should I change this from delta G naught to delta H naught minus T delta S naught? Do I have to do that? No, I don't have to do that because this is delta G naught at temperature T. T is 298 Kelvin, so this is the correct delta G naught and the temperature is correct. And so this is fine to use this equation, and we end up with what?
I got 1.845 times 10 to the negative
1.485 times 10 to the negative
1.845.
1.845 times 10 to the negative 23rd.
Yes.
This is equal to K, which is equal to the pressure of O2 to the 1/2. And so the pressure of O2, we'd square both sides. So go ahead and square that.
3.407 times 10 to the negative 46.
And the units for this would be bars or atmospheres. A bar and an atmosphere are close. Exactly. And so alternatively, what we'd have to do is we'd have to hook up a vacuum pump. And at 298 Kelvin, if we can pump down the external pressure, so we put our copper 2 oxide here, solid, and then we want to create a vacuum here. And the vacuum that's going to be required will be 3.4 times 10 to the minus 46 bars. Is that an easy pressure to achieve with the vacuum pump? Well, I mean, how would you say 10 to the minus 46? What would that be? It's not a microbar, is that? Microbar, actually millibar is no problem. We can pump down a millibar easy. Microbar is getting more difficult. But this is way beyond that. Right? And so this is, forget it. You know, that's too low of a pressure. And so probably the best method is a combination of lowering the pressure and elevating the temperature. And so let's try that. This is extreme. Too extreme here. Spelled, let's do misspelling. Yeah. All right, let's try a combination of both. Raising the temperature and lowering the pressure. And so what kind of vacuum can we generate easily here? About, let's say 0.5 atmospheres. I'd like to measure this. It's more like 0.9, but we should be a little bit more generous because the vacuum pump should easily be able to pull half. So what we'll do is we'll set the pressure of O2 to about half an atmosphere, or half bar. This is about a half an atmosphere. And then solve for the temperature. So this means that we don't have to go as extreme as far as temperature goes, or vacuum, hopefully. And so what equation do I use for this? Standard or non-standard? Non-standard, so we want delta G is equal to delta G under standard conditions plus RT ln of Q. And what I want to do is I want to make this go from spontaneous to non-spontaneous. The way to do that is to go through 0. And so I'll set this equal to 0. Delta G is equal to 0, which is equal to delta G naught plus RT ln of K. Because when delta G is equal to 0, we're at equilibrium. But there's a problem here. And the problem is that delta G naught depends on temperature significantly. Now we're changing the temperature. Is it okay to use delta G naught? No. So I'm going to go ahead and insert this here. Actually, not here. Let's solve. Delta G naught is going to equal minus RT ln of K, which equals delta H naught minus T delta S naught. And so delta G naught is a strongly dependent on temperature. But when I look at these terms here, these aren't as strongly dependent on temperature. And so we'll get the temperature on one side, that is T delta S naught, which is going to equal, T delta S naught minus RT ln of K is equal to delta H naught. And then solve for T. T is equal to delta H naught divided by delta S naught minus R ln of K. And so now we have this data at 298, and we're going to make the assumption that the data at 298 is close to the data at the temperature whatever we calculate. It would be better to have the delta H and delta S values for that temperature, but we don't. It's impossible. All right, so delta H was the 129.7, what was it? Okay, I'm going to convert this into joules, so 129,700 joules. Delta S was 24.9 joules per Kelvin. R, 8.3145 joules per Kelvin. ln of K. K is What's the partial pressure of O2 we're going to generate with our vacuum?
25.
0.5. And then the O2 has to be raised to the 1/2 power. Because K is going to be, this is G raised to the little g power. And the temperature comes out to
Is it 4668.5?
4668.5. All right, under standard conditions, we have 1 atmosphere, right? If we pump down on it to a 1/2 an atmosphere, it helps because under standard conditions, the temperature we had to achieve was what? What was the temperature we had to achieve under standard conditions? Under standard conditions, the temperature we had to achieve, wasn't it 1600 roughly?
Yeah.
1700 Kelvin. Now we have some vacuum helping us. The vacuum should be helping us, making it easier, but this number doesn't quite match. Something's wrong. Because the vacuum should mean we don't have to go to as high of a temperature, but now it looks like we have to go to a much higher temperature. And so there's a calculation error. Which calculation is wrong? Our earlier calculation or this? One of them can't, both of them can't be right. One of them has to be wrong. And so what we need to do is we need to go back and double check our previous calculation, the one where we changed delta G naught. In other words, our previous calculation was the calculation temperature is equal to delta H naught over delta S naught. And so we should double check that. Can somebody double check that calculation? Delta H naught was 129,700. Delta S naught is 24.9. Uh-huh.
Is that 0.5 to the 1/2 power? Or is that L of 0.5 to the 1/2 power?
0.5 to the 1/2 power, and then natural log. Or you can bring the 1/2 in the front. Do you get the same numbers? All right, from our previous calculation, this is just doing it without using a vacuum pump. Without using a vacuum pump, let's just double check that calculation. That calculation was 129,700 divided by 24.9.
Delta H value is wrong. But you put in delta.
Oh, what is the delta H value?
It should be
157.3 kilojoules. Okay. Yeah, sorry about that. Let's check this calculation.
Oh, 5.66? They're getting worse.
It's getting worse. 157,300 joules. So 157,300 joules divided by our delta S, which is 24.9.
5,660.
Yeah. The first calculation was wrong. Did I use the wrong delta H in the first calculation? 157.3 kilojoules divided by 24.9 joules per Kelvin gives me 6,317 Kelvin. 317 Kelvin, is that a temperature we can achieve easily? No. And so without using a vacuum pump and just using a furnace alone, what kind of furnace is going to heat up to this number? You know, a methane air flame burns at about 800 degrees C. Is that even going to be hot enough? Nowhere near hot enough.
Wait, before delta S was 0.0930. How do we get that? Wrong delta.
Did I use the wrong delta F?
What is it?
93.03. Okay, thanks. 93.03. That's right. And so this should be 93.03. I shouldn't erase it. I should write it up there.
It's worse now. It's like 52,000. Oh, 93.03, not 0.92. Okay, 1,688.
1,688 Kelvin. All right. 1,688 Kelvin. All right, what does this one come out to?
Oh, no, I meant that one.
Oh, this one?
Yeah.
1,688 Kelvin. This is with vacuum. This one is without vacuum. 1690. Okay. Wow. Did the half an atmosphere vacuum help us?
Yes.
Yeah, we don't have to heat it nearly as hot, right?
Yeah.
Only to 1688 Kelvin rather than 1690 Kelvin. And so basically this reaction is going to be difficult to achieve. Right? It's going to be difficult to make spontaneous using the current. You know, some reactions are just impossible to make spontaneous. You know, the math just doesn't work out. But this one is theoretically possible. Even though this one's theoretically possible, you know, to achieve these temperatures is going to require a lot of energy. In this case, it's not even worth adding the vacuum. It doesn't help that much. Assuming the calculations are good and the data is correct. And so it looks like we're out of options. We're going to have to pay to heat these up to extreme temperatures, but we aren't, because there's one more option, and the last option is maybe the first one to go with, and that is coupled reactions. Coupled reactions is just an application of Hess's law. And that is, if we have this reaction, which is highly unfavorable, with a delta G, what was the delta G again? Was it the delta G that was 129?
Yeah.
All right. That's what it was. 129.7 kilojoules. That's highly unfavorable. What we can do is we can add a second reaction to this with a delta G naught that's going to be less than minus 129.7 kilojoules. And so what that's going to do is it's going to cancel this one out and then make the whole thing negative. So that when we add these two up to get the net reaction will have a delta G naught that's going to be less than 0. That's what we want. And so what is the reaction we're going to add to this? Well, the reaction we're going to add to this is going to be something that either attacks copper or attacks oxygen. Well, let's say the reason I want to do this is this. Have you ever noticed you know, pennies will blacken with age. And so if you look at a penny, the surface becomes oxidized. Well, if you want a shiny penny, how can you get a shiny penny back?
Like put lemon juice or something?
Put some lemon juice on there,
Vinegar.
vinegar or lemon juice, because the coating on here is copper 2 oxide, a black coating, plus vinegar, which is acetic acid, is going to give us what? It's going to give us copper 2 acetate plus H2O liquid. What kind of reaction is this? This is an acid-base reaction or a metathesis reaction or a double replacement reaction. The driving force is going from stronger acid, acetic acid, to weaker acid, water. But there's one problem with this, and that one problem is this. If we were to eat up the black coating here and make the penny shiny again, do we still have the same amount of copper metal? No. In fact, we're going to lose copper metal. This is going to be washed off in the solution. So, you know, to not lose any copper metal, this is better, because when what we're going to do is we're going to chemically convert the black coating back into copper metal. That way we don't lose any copper. This is important. I mean, you know, let's say you have silver and the silver's tarnished. Well, you can get some cloth and sand it off, you know, the tarnish, or polishing compound and polish it off, but the end result is you're going to lose silver, right? And so what we want to do is we want to reverse that, you know, oxidation and regenerate the original metal. And so what we want to find is something that attacks oxygen. What attacks oxygen, or what lights oxygen? I'll tell you what really likes oxygen: hydrogen. If I mix hydrogen gas with 1/2 O2 gas, I'm going to form H2O liquid. And so if I can react the O2 that's formed here, the net reaction is going to look like this. It's going to be CuO solid plus hydrogen gas yields Cu solid plus H2O liquid. So instead of reacting it to form oxygen, we sacrifice this, so there's a bit of a compromise here. We aren't going to get the exact same products, but we're interested in the copper and recovering as much copper as possible. And so if we don't care about the O2, O2 is also a valuable reagent. If we don't care about the O2, we can just convert that into water by adding hydrogen. Hydrogen, is it very expensive? No, not very expensive. And lots of ways to produce it. And so this could be a lot cheaper than, you know, buying a fancy furnace or buying a powerful vacuum pump, or both. And so what we need to do is we need to figure out what is delta G naught for this. Well, what kind of reaction is this? This is called a formation reaction. It's formation of H2O liquid from the elements in their standard state. And so delta G naught for this is just equal to delta G naught of formation for H2O liquid. What is delta G naught of formation for H2O liquid? Can somebody look that up? Negative 237.1 kilojoules. And so you see the 129.7 is easily going to be negated by this. And not only that, it's going to make this whole thing. So Hess's law says we just add the energies. And so 129.7 minus 237.1 is equal to minus 107.4 minus 107.4 kilojoules. What does that tell you about the net reaction here? Highly exothermic and highly spontaneous. And so this is at 298 Kelvin. So the simple way of making this spontaneous at 298 is to do a coupled reaction. We don't have to heat it up. And this should be spontaneous with a pretty big driving force at room temperature. But we're going to have to add hydrogen, which is going to be additional cost, and we're going to lose oxygen, which might be an additional cost, depending on what you want for product. So this is the idea behind coupled reactions. Coupled reactions happen a lot in biology. You know, all the tricarboxylic acid cycle, Krebs cycles, all that. You're looking at coupled reactions, forming higher energy molecules from lower energy. Okay, now let's take a look at this reaction. You know, even though it's spontaneous, that's what we call a thermodynamic driving force. It's spontaneous, but is the reaction going to happen instantaneously? You know, the moment I mix the hydrogen with a copper-2 oxide, you see the reaction occur? Now, we have to look at the kinetics of the reaction. And usually there's going to be some kind of activation barrier. And so when we're looking at thermodynamics, we're looking at the state function. The state functions would be the final state versus the initial state. We see that delta G is highly exothermic here. And so when we look at G, here's our initial, here's our final. But in order to get from our initial state to our final state, we have to overcome some kind of activation barrier. And so this mixture might be metastable as well. All right, so let's take a look at this reaction here.
This experiment enables us to find the formula of copper oxide by reducing it in a stream of hydrogen. The hydrogen removes the oxygen and forms water, which will be steam at the temperature of the experiment. This is the apparatus we use, a pilot reduction tube, which is essentially a boiling tube with a small hole in the end to allow excess hydrogen to escape. Before starting the experiment, it's important to familiarise yourself with how to use a hydrogen cylinder. This valve here, the cylinder valve, is operated by a spanner. Turning the spanner allows hydrogen gas into the pressure reduction valve here.
Pressure reduction valve is also called a regulator. What he's doing is he's opening the valve by turning it clockwise, so it's backwards.
That gauge there. And finally, the flow rate of the hydrogen is regulated using this needle valve
There's a little needle valve there.
here. We first need to weigh the empty reduction tube.
Okay, this is an experiment, so I'm going to fast forward through some of this stuff here.
into the reduction tube.
This is copper 2 oxide.
Try to place this in the center of the tube. It's too close to the hole end, heating the bung while we heat the copper oxide. I put the copper oxide into the tube. We reweigh it. Desiccator. The rate of flow that you can just feel on your cheek is about right.
It's adjusting the flow rate for.
Now
Hydrogen.
the hydrogen delivered to.
This is probably not the way you want to adjust it, though. But looks like he took a good whiff of the hydrogen.
The next step is to light the hydrogen, but it's important to wait for about a minute to make sure all the hydrogen is flushed out.
So what he's doing is flushing the air out of the.
Otherwise, you could get an explosive mixture in there. For the lighting process, we have safety screens to protect the demonstrator.
Yeah, unfortunately, we don't have that.
And
We use that to protect the audience.
All right.
Otherwise, I'd do it.
Well, at least you have the.
This is a reaction I've done before, but I didn't ignite it at the end here. I just let the hydrogen bleed out.
Something like a minute has passed without light the hydrogen.
But this is interesting because he scrubs the excess hydrogen by burning it. The hydrogen has this red flame.
3 centimeters or so. At this point, there's no more explosion risk, so we can dispense with the safety screens.
So right now, the delta G is highly favorable, right?
Yeah.
This reaction should be spontaneous, but do you see much reaction occurring? No, that's because of the activation. This is called metastable mixture. So
If you just be on the blue color.
one way to speed it up is to heat it. You know, if there's air inside here, it would explode, but there's no air.
Activations can be made. These will probably need to be pointed out to the audience. Droplets of water will condense on the cooler part of the reduction tube near the hole.
He has a lot of copper 2 oxide in there. That's why it's reacting so much slow.
The height of the flame will drop as some of the hydrogen is used up, reacting with the oxygen in the copper oxide. The flame may develop a green coloration caused by copper atoms vaporized into the flame. Use the Bunsen burner to chase the glow along the length of the oxide until all the black copper oxide has been changed to pinkish copper. This will take up to a minute. When no trace of black remains, continue to heat for at least a further minute to ensure that all the oxide on the inside of the heap has reacted. If in any doubt, continue heating for longer. Make sure any condensation has evaporated. When you're confident that all the copper oxide has been reduced, the flame is back to its original height, you can stop heating. It's now important to leave the apparatus exactly as it is with the hydrogen flowing. This is to prevent air from diffusing back into the reduction tube and converting some of the hot copper back to the oxide. Continue until the tube is cool enough to touch comfortably. We now blow out the flame, remove the hydrogen delivery tube and turn off the cylinder.
Usually you don't just turn off the needle valve. The needle valves typically leak. And so you turn off the regulator here for the main valve. He's weighing it.
The copper looks pinkish and not particularly metallic. If students are not convinced that it actually is metallic copper, it's possible to show it out of the tube and use a circuit tester to show that it is in fact metallic. Finally, we have to turn off the hydrogen cylinder. We first close the cylinder valve with a spanner, and we then need to use the pressure reduction valve, turn it on, and the needle valve on to vent any hydrogen from the valve here. Finally, turn off the pressure reduction valve and also the needle valve.
All right, there are different types of reactions though that are encountered. You know, some reactions will have a pretty big activation. This reaction had a pretty big activation barrier, right? But there are other reactions that react immediately when things are mixed, like pyrophoric substances. Pyrophoric substances, you know, the minute they come into contact with whatever reactant you're reacting with will react, and it could react violently. Pyrophoric materials typically come into contact with air and then spontaneously combust into flames. And so that has a very, very low activation barrier. And so you got to be careful. You know, some things will react violently upon mixing. Other things you have to heat to get going. And so even though we saw this huge delta H, I mean not delta H, we saw this huge delta G, which is highly favorable, right? It didn't react right away at room temperature. It required some oomph to get over that hump. All he had to do was get it initiated and then just let it go. The kinetics will tell us how fast it goes. So, you know, you got to be careful because these can be deceptive, and you can have some reactions which don't even have this much driving force, which are incredibly violent because of that low activation barrier. And so this is why when we're looking at chemical reactions, we consider two things. We consider the thermodynamics of delta G, and then the kinetics. You know, how big is that hump to get over? This is like a fence. You know, we got this huge cliff here, and so if you're going to fall down the huge cliff, no problem. But if you got this fence stopping you, then you aren't going to fall down the cliff. You need some kick to get over that fence. All right, so we'll stop here, take another break, and then we're going to start the lab next. Okay.